So let's look at another example of finding the arc length of a curve. So here I have y equals log of 1 minus x squared, where x is between 0 and a half. So I'm going to apply my arc length formula. So I'm going to have L is equal to the integral from 0 to a half of the square root of 1 plus y prime squared dx. Okay, so I'm going to go through and figure out what y prime is, then what y prime squared is, and then what 1 plus y prime squared is before I go inserting anything into my formula. So notice that y prime will be the derivative of this log function here. It'll be 1 over 1 minus x squared times negative 2x. Okay, so we go to find what y prime squared is. I'm going to have negative 2x over 1 minus x squared squared. Okay, which gives us 4x squared over 1 minus x squared squared. Okay, and then I want to think about, well, what is 1 plus the derivative squared? Okay, so a lot of times finding the 1 plus the derivative squared part requires getting a common denominator. So I can combine those different pieces and then look for trying to turn it into something squared. So I have 1 plus 4x squared here over 1 minus x squared squared. So the common denominator I need is this 1 minus x squared squared. So I'm going to have 1 minus x squared squared plus 4x squared all over 1 minus x squared squared. Okay, so we want to look at combining some of these terms that are in the numerator. So I'll distribute out this 1 minus x squared squared. So I see that that's 1 minus 2x squared plus x to the 4th plus 4x squared all over 1 minus x squared squared, which gives me x to the 4th plus 2x squared plus 1 over 1 minus x squared squared. Okay, I notice that my numerator here, this x to the 4th plus 2x squared plus 1, can be factored into x squared plus 1 times x squared plus 1. So I have x squared plus 1 squared over 1 minus x squared squared. Okay, notice x squared plus 1 times x squared plus 1 will give me x to the 4th plus x squared plus x squared plus 1. So I do get what I have over here on the left. Okay, so we have all that initial work here, and now I can write down that my arc length is the integral from 0 to a half of the square root, and I'll write the 1 plus form first here. So I have 1 plus my derivative squared. Okay, so that turned out to be 4x squared over this 1 minus x squared squared. And then with the work, that we did over here, we see that this is the square root of x squared plus 1 squared over 1 minus x squared squared dx. Okay, so now I have to be a little bit careful, at least think carefully about what I'm doing. So I know that the square root of something squared is defined to be the absolute value. Okay, so for the numerator, x squared plus 1 is always positive, so the absolute value of x squared plus 1 would also be x squared plus 1. So I do have x squared plus 1 in the numerator. The denominator would be the absolute value of 1 minus x squared when I undo the square root. And then I just want to think about whether 1 minus x squared is actually positive over this interval from 0 to a half. Okay, so let's just think about where 1 minus x squared is positive and where it's negative. So notice that 1 minus x squared is 0 when x is 1 and negative 1. So I can just go over here and think about, this is just a little scratch work over to the side. So it's 0 at negative 1 and 1, so we want to see where it sort of changes signs here. So if I plug in something less than negative 1 into 1 minus x squared, like negative 2, then I would have 1 minus negative 2 squared, or 1 minus 4, so that would definitely be something negative. I plug in something between negative 1 and 1, like 0, that would be positive, plug in something bigger than 1 like 2, I'm going to get something negative for 1 minus x squared. But fortunately I'm dealing with values here between 0 and a half, so I'm living in this space where 1 minus x squared is positive. So I can go ahead and drop those absolute value bars without adding a negative sign to that, because remember the absolute value of x is equal to x when x is greater than or equal to 0, and negative x when x is less than 0. Okay, so we just made sure that we could simplify this as just 1 minus x squared in the denominator. Okay, so now we're ready to think about integration techniques. So notice what I got here is a rational function. Okay, but is it a proper rational function? Well, I have the degree of the numerator is 2 and the degree of the denominator is 2. So it's in fact improper. Okay, to be proper, you have to have the degree of the numerator being strictly less than the degree of the denominator. So let's look at doing some long division here. So I have x squared plus 1 divided by 1 minus x squared. Okay, that's going to go into x squared plus 1 negative 1 times. So multiply negative 1 times this, I have x squared minus 1. We're going to subtract that out. I have 1 minus a negative 1, or 1 plus 1, so I have a remainder of 2. So I see that x squared plus 1 over 1 minus x squared is equal to negative 1 plus 2 over 1 minus x squared. Okay, and now we have a couple of options in terms of how we want to integrate 2 over 1 minus x squared. So one option would be to use trig substitution. Another option would be to do partial fractions on 2 over 1 minus x squared. Okay, so we can use trig sub or partial fractions. And I'll go ahead and use partial fractions here. Okay, so you see how our integration techniques that we've learned earlier are going to come back within these applications that we're learning. So notice that 2 over 1 minus x squared would be equal to a over 1 minus x plus b over 1 plus x. Since 1 minus x squared factors into 1 minus x and 1 plus x. So I would have, when I clear the fractions, 2 is a times 1 plus x plus b times 1 minus x. Okay, so let's plug in some convenient values here. When x is negative 1, we would have 2 is equal to b times 1 minus a negative 1, or times 2. So we see b is equal to 1. If I plug in another convenient value of 1, I see how we get 2 is equal to 2a. So a is also equal to 1. Okay, so going back up here, I see I can be looking at an integral from 0 to a half of negative 1 plus 1 over 1 minus x plus 1 over 1 plus x. Okay, so now I have three terms whose antiderivatives are much simpler to find. Okay, so we'll have negative x plus log of the absolute value of 1 minus x. Remember, I have to divide by the derivative here that I would have for 1 minus x, or divide by the that linear constant. So this is going to be divided by negative 1 times negative 1. Just reminding ourselves we have this particular rule. Okay, when I have the integral of 1 over a plus bx dx, this is equal to log of the absolute value of a plus bx all over b plus c. Okay, that rule is specific to having 1 over something linear. Okay, so I have this negative log 1 minus x plus log of 1 plus x plus, oops, not plus c, I actually have to plug in my bounds here. So when I plug in my bounds, I have the integral from 0, or excuse me, I'm evaluating this from 0 to a half. So we have negative 1 half plus negative log 1 minus a half, so that'll be 1 half here, plus log of 1 plus a half, or 3/2. And this will be minus 0. And then I'll have plus log of 1, which is 0, log of 1 again, which is 0. Okay, so we're almost ready to simplify this and get to our final answer. Okay, so what I have here is a complete answer for the arc length, but it might be nice to just write it a little bit more concisely. So notice that with log rules, this negative log 1/2 could be written as negative log 2 to the negative 1 or positive log of 2. So recall some log rules here. The log of x to the r is equal to r log x. Okay. So when I have this 1/2, that's like 2 to the negative 1 power, so the negative 1 can come out in front times this negative 1. So that's plus log of 2. We also know that log of some a over b is equal to log a minus log b. So that log of 3/2 can be written as log 3 minus log 2. So you see how that helps us out a little bit. These two cancel. So our arc length simplifies to negative 1/2 plus log 3. Okay, so I realized that this was a very involved example. We're trying to show kind of a range of different types of problems. Not all of them will be this involved, but now you've seen one that involves multiple techniques, partial fractions, doing some long division, etc. Let me know if you have any questions on these examples.